turn goes with the Philippine Airlines DC-8 jet, bound for Manila to complete the inaugural flight of the new twice-weekly service between Sydney and the Philippines.
Good day, Engineer Disquitado, and to my fellow classmates. I am Janelle Adrian Rodriguez. Together with Group 4, we will be discussing inertia forces and load factors. Here are our members and the topics to be discussed. The first one is Introduction, Parallel Axis Theorem for an Area, Moments of Inertia, which will be discussed by yours truly. The second one is Inertia Forces, to be discussed by Nomura. The third one is Inertia Loads, which will be discussed by Olos. The fourth one is Load Factors, to be discussed by Paz. The fifth one is Equilibrium of Aerodynamic and Structural Force, which will be discussed by Ramos. Lastly, Problem Solving, to be discussed by Padua and Rosario. Now, let's have a recap on our topics during high school. So, these things are just to recap and remember in order to have a further understanding of inertia forces. So, we all know who Sir Isaac Newton is. His first law states that every object remains at rest or in uniform motion in a straight line unless compelled to change its state by the action of the external force. He also said that an object will continue to be in state of rest or in a state of motion unless an external force acts on it. Now, there are three types of inertia. The first one is inertia of rest, where an object stays where it is placed and it will stay there until you or something else moves it. As you can see in this illustration or in this example, this is a great example of the inertia of rest, where the tendency of an object stays at rest is shown. As you can see the coin there. And next we have is inertia of motion. So in inertia of motion, an object will continue at the same speed until a force acts on it. And lastly we have is inertia of direction. So in inertia of direction, it is where an object will stay moving in the same direction unless a force acts on it. As you can see in this one, it is heading in the same direction. So it is going downwards until there was this block that topped it. So it is like in the inertia of direction where an object will stay moving in the same direction unless a force acts on it. Moving on to the moments of inertia. So whenever a distributed load acts perpendicular to an area and its intensity varies linearly, the calculation of the moment of the loading about an axis will involve an integral of the form integral of y squared dA. So for example, consider this plate in figure 10-1, which is submerged in a fluid and subjected to the pressure P. So the pressure varies linearly with depth. So given the equation will be P is equal to gamma times y. So where gamma is the specific weight of the fluid. So thus, the force acting on the differential area dA of the plate is therefore dF is equal to P times dA equals gamma times y multiplied to dA. So the moment of this force about the x-axis is therefore dm is equal to y dF equals gamma times y squared dA. So by integrating dm over the entire area of the plate yields m is equal to gamma the integral of y squared dA. So basically the integral of y squared dA is sometimes referred to as the second moment of the area about an axis, which is the x-axis. But more often, it is called the moments of inertia of the area. So the word inertia is used here since the formulation is similar to the mass moment of inertia, which is the integral of y squared dm, which is a dynamical property. By definition, the moments of inertia of a differential area dA about the x and y axis are di sub x is equal to y squared dA and di sub y is equal to x squared dA, respectively. So for the entire area A, the moments of inertia are determined by the integration of I sub x is equal to the integral of y squared dA with the lower limit of area, and I sub y is equal to the integral of x squared dA with the lower limit of area. We can also formulate this quantity for dA about the pole O or z-axis as shown in figure 10-2. So this is referred to as the polar moment of inertia. Therefore it is defined as dj sub O is equal to r squared dA, where r is the perpendicular distance from the pole z-axis to the element dA. So for the entire area, the polar moment of inertia is therefore j sub O is equal to the integral of r squared dA with the lower limit of area equals I sub x plus I sub y. So this relation between j sub O, I sub x, and I sub y is possible, since r squared is equal to x squared plus y squared. From the formulations that is given, we can see that I sub x, I sub y, and j sub O will always be positive, since they involve the product of distance squared and area. Therefore, the units for moment of inertia involve length raised to the fourth power. Take note of that. So, such as meter raised to the fourth power, millimeter raised to the fourth power, or feet raised to the fourth power, and inches raised to the fourth power. Moving on to the parallel axis theorem for an area. So the parallel axis theorem can be used to find the moment of inertia of an area about any axis that is parallel to an axis passing through the centroid and about which the moment of inertia is known. So in order to further develop this theorem, we will consider finding the moment of inertia of the shaded area shown in this figure 10-3 about the x-axis. So to start, we need first to choose a differential element dA located at an arbitrary distance of y prime from the centroidal x-axis. So if the distance between the parallel x and x prime axis is d sub y, then the moment of inertia of dA about the x-axis is therefore di sub x is equal to y prime plus d sub y squared dA. So for the entire area, it is equivalent to I sub x is equal to the integral of y prime plus d sub y squared dA with the lower limit of area. And when we integrate further, we get the integral of y prime squared dA with the lower limit of area plus 2 dy integral of y prime dA with the lower limit of area plus d sub y squared, the integral of dA with the lower limit of area. So the first integral represents the moment of inertia of the area about the centroidal axis, bar I sub x prime. So the second integral is 0 since the x prime axis passes through the area's centroid C. So since the third integral represents the total area, the final result is therefore I sub x is equal to bar I sub x prime plus a times d sub y squared. So a similar expression can be written for I sub y, which is equal to a bar I sub y prime plus a sub v x squared. And finally, for the polar moment of inertia, since bar j sub c is equal to the bar I sub x prime plus the bar of I sub y prime, and d squared is equal to d sub x squared plus d sub y squared, we can get j sub o is equal to bar j sub c plus a times d squared. Take note that the form of this is the form of each. These three equations states that the moment of inertia for an area about an axis is equal to its moment of inertia about a parallel axis passing through the area's centroid plus the product of the area and the square of the perpendicular distance between the axes.
Inertia forces. Inertia is a property of a body by virtue of which it opposes any agency that attempts to put it in motion, or if it is moving, to change the magnitude or direction of its velocity. Inertia is a passive property and does not enable a body to do anything except oppose such active agents as forces and torques. We can define inertia as the property of an object by which it cannot change its state of rest along a straight line on its own, unless acting upon by an external force. Inertia increases with an increase in the mass of the body and vice versa. There are three types of inertia. First one is inertia of rest. It refers to the inability of a body to change its state by itself. For example, when we shake the branches of a tree, the limbs fall because the components they are attached comes into motion. On the other hand, the limbs tend to be at rest and hence get detached. The inertia of motion. It refers to the inability of a body to change its state of uniform motion by itself. For example, when a moving car suddenly stops, the person sitting in the car falls forward because the lower portion of the body contact with the vehicle comes to rest. In contrast, the upper part of the body tends to remain in motion due to the inertia of motion. Lastly, inertia of direction. It implies that the body cannot change its direction of movement by itself. For example, when a car takes a curve, the person sitting inside thrown outward to maintain his or her direction of motion. This phenomenon happens due to the inertia of direction.
Good afternoon. My name is John Clarence Diolos, and my topic will be about inertial loads. To be specific, its meaning and definition, as well as its examples, application, and equations. Now, inertial loads are the maximum load on any given part of an aircraft structure that occurs when the aircraft is in acceleration. The loads produced are the landing impact, maneuvering, gust, boost, and staging operations, launches, and dockings, which are always greater than that of the loads occurring when all forces upon the aircraft are in equilibrium. It is important to determine inertial loads acting on the aircraft before going on to any design regarding structural components. Now, below are the overview of types of loads, in which these are the specific examples of inertial loads, namely the acceleration, rotation, dynamics, vibration, and lastly, flutter. Moving on, while there are a lot of loading conditions, an aircraft may be considered as being pure translation or pure rotation. The inertia force on any given mass is equal to that of the product of the mass and the acceleration, which also acts in the direction opposite to the acceleration. M is referred to the mass and A is the acceleration. relative to the Newtonian frame or reference. This is showcasing inertial load in its simplest form, which is F is equal to m times a. Now, if a Cartesian system of x, y, and z axes were to be chosen in this frame, then it would resolve into components and look like this, which is the f sub x is equal to mx, f sub y equal to my, f sub z equal to mz, where f sub x, f sub y, and f sub z are the components of f along the respective axes. At the same time, x, y, and z are the components of acceleration along the x, y, z axis. Now, in many cases where the elements of a rigid body are moving in curved paths, they are moving in such a way that each additional inertial forces AR derivative of m acting perpendicular to r and opposite to the direction of acceleration. This force has components zx derivative of m in the y direction and a y derivative of m in the x direction. Now looking back at the figure, the resultant inertia force on the entire body in the x direction would look like this. F sub x is equal to integral of a y derivative of m equals to integral y derivative of m equal to 0. At the same time, for the resultant inertia force in the y direction would look like this. Now, the resultant inertia torque about the axis of rotation is obtained by integrating the terms regarding the product of the tangential force on each element, AR derivative of m, and its moment arm r, which would look like this. P sub O integral of AR squared derivative of m equals to A integral r squared derivative of m equals to A I sub O. Now, you can see in the equation we have I sub O. The term I sub O represents the moment of inertia of the mass about the axis of rotation. This moment of inertia can be transferred to a parallel axis through the center of gravity by using the following relationship, which is I sub O equals to mx squared plus I sub c. In the next equation, regarding the inertia of the mass about an axis through the center of gravity, the term I sub c is obtained as the sum of products of mass elements derivative of m and the square of their distances rc from the center of gravity, which would look like this. I sub c is equal to integral of r squared sub c derivative of m. Lastly, by substituting the value of I sub o from the I sub o equation in the inertia torque equation, we get the following expression for the inertia torque, which is T sub O is equal to mx squared A plus I sub c multiplied to A. That's about it for my part. Thank you.
My name is Joseph Crisal de Paz, and for today's topic, I will discuss just a brief introduction about load factors. One might wonder what the load factor really is. As it says here, the load factor is the ratio of the aerodynamic force on the aircraft to the gross weight of the aircraft. In layman's term, it is the ratio of the aircraft's lift to its weight. That's why on normal and steady flight, the formula here, N, which represents the load factor, is equal to L divided by W, which represents lift and weight respectively. Since it is the ratio of two forces, it is dimensionless, but traditionally we use G forces or G as its units because of the relation of the load factor and the acceleration of gravity within an aircraft. To put it simply, 1 G is just equal to the weight of the aircraft, and 2 G's is equal to twice the weight of the aircraft, 3 G's is thrice the weight, and so on and so forth. It is called the load factor because it is a measure of the forces or loading impressed on the structure or occupants. If the load factor exceeds the tolerances of the structures or occupants, temporary or permanent damage can occur to the aircraft. That's why there are two types of load factors factored into an aircraft design: limit load and ultimate load. Limit load is a force applied to an aircraft that causes a bending of the aircraft structure that does not return to the original shape, while the ultimate load is the load factor applied to the aircraft beyond the limit load and at which point that the aircraft material experiences structural failure or breakage. Load factors lower than the limit load can be sustained without compromising the integrity of the aircraft structure. So here, for a normal straight and level flight, as we can see on the figure on the bottom left, the aircraft's lift force, or what we call here the vertical lift, generates enough force to oppose the weight of the aircraft, making lift equals to weight, and N or G force would be equal to 1. Hence, make 1 G force for a normal steady flight. But it is quite different story if it involves roll or bank angle. For example, on the figure on the bottom right, we can see that now it involves turning. In this case, some of the lift will be pointed horizontally that will produce centrifugal force. Now combining that centrifugal force along with the weight, we would gain the resultant force or the load. To calculate the load factor for a certain bank angle, we would want to use the formula that can be seen on the slide. N or G equals to 1 over cosine the bank angle. So if we apply that for 60 degrees bank angle, then if we calculate it, the G force acting on the aircraft would be 2. Meaning that just on what I just said before, that the aircraft and its occupants would experience 2 times or twice the force of gravity. So just for the general reminder, in a steady flight, the load factor would always be equal to 1. If an aircraft is in climb, the load factor is greater than 1. And as for descent, load factor will be less than 1. And lastly, in case of a roll or turn, the load factor will be determined by the bank angle of the aircraft.
I am Emmanuel Christian C. Ramos, and I will be discussing one of the subtopics of inertia forces and load factors, the equilibrium of aerodynamic and structural force. To examine the performance, control, and stability of a proposed aircraft, extensive aerodynamic data is necessary. Only the information necessary for the structural analysis is examined here, despite the fact that this would ordinarily be gathered as a part of a larger program. The lift, drag, and pitching moment force distributions for the entire aircraft with horizontal tail removed over the range of angles of attack from the negative stalling angle to the positive stalling angle are the initial aerodynamic data necessary for structural analysis. Because of unpredictable effects of aerodynamic interference of multiple components, equivalent data for the combination of wing and fuselage, or the wing, fuselage, and nacelles is difficult to compute precisely from available information. Wind tunnel experiments on a full airplane model without an horizontal provide lift, drag, and pitching moment data for all angles of attack. The components of the lift and drag forces are then computed in relation to the aircraft reference axis, as indicated in Figure 2.3. The airplane axis can be selected. The force components are C sub x qs and C sub z qs along this axis, where q is equal to p v squared over 2 is the dynamic pressure and s is a surface wing area. The non-dimensional force coefficient C sub z and C sub x are calculated using the following equation to project the lift and drag coefficient for the airplane without a horizontal tail along the reference axis. The angle is measured from the flight path to the x-axis as shown in Figure 2.3 and is equal to the difference between the angle of attack and the angle of wing incidence. The balancing air load on horizontal tail Q sub TQS is obtained from the assumption that there is no angular acceleration of the airplane. The moments of the forces shown in Figure 2.3 about the center of gravity are therefore in equilibrium motion, where C sub t is a dimensionless tail force coefficient expressed in terms of the wing area and L sub t is the distance from the airplane's center of gravity to the resultant air load on the horizontal tail, as shown in figure 2.3. Since the pressure distribution of the horizontal tail varies according to the altitude of the airplane, L sub 2 theoretically varies from different loading conditions. This variation is not great, and it is customary to assume L constant by using a conservative forward position of the center of pressure on horizontal tail. The total aerodynamic force on the airplane in the z direction, C sub z sub O qs, is equal to the sum of the force C sub z qs on the airplane less tail and balancing tail load C sub t qs.